Okay, so I'm just going to walk through how to download the starter code and how to get started with it. So I'm going to share my screen. The lecture for today, so yeah, wave file format. So right here, wave parser code. So right here, it says my code. This is my solution that I've coded up. And if you ever want a reference or want some help, then then like all the solutions of how to load everything is here. But this is how you download the starter code. So you just click on this and it'll download this, this zip file. And so I've already extracted this zip file right here. So now, I've opened up the zip file in Visual Studio Code. And if we try to just run this, so here I have my terminal. And as you can see, I have it running bash. So you want to make sure that this is bash. And you can get bash by just installing git bash. So git bash. So go and download and install git bash. And then once you do, then you'll have access to bash. And once you have access to bash, then you can just run the command make. And make will run all the commands that are in this make file. And I won't go into how make files work, but we do need to edit this make file before it actually works. So as you can see here, we're actually getting some errors, like undefined reference to whatever. And it's because we need to make sure that we uncomment the correct compiler flags. So if you are on Windows, then you want to uncomment these commands or these flags. And if you're on macOS or Linux, then you want to uncomment these commands. So so once you go and uncomment the commands or the flags that that you need, then you save it, close out, and then now when you run make, then it should work. Okay. And we're getting a warning here because you need to go and just implement whatever function is throwing this warning. It's confused. So here is my code that is currently on the repository. And so step one, so you have to uncomment the makefile flags and then run make. Or you can run the command that I provided. And so once you run make, then you get this main.exe, or if you're on Unix, then you'll get main. And now you can do /main. And now you can open up a wave file after that. So I have this tests folder, and it has a bunch of different tests that you can do. So you can try like sign left, and you can open it, and then now it will go and print out a bunch of information about it. So we can see, it says like riff, format, data, whatever, then prints like a bunch of just random data, and then prints some more data. And so this is in theory, hopefully, this is what you will be doing today, is having it load in all of the correct data, or so that you can see what's in the file. Cool. Okay, so that's what we'll be doing today. But first, I want to show you what a wave file actually looks like. So here is sign both. So it's currently, it's this file right here, sign both. And if we want, we can open it. In a hex editor. But it's super weird. Like, what the heck does any of this mean? Who knows? But one thing I noticed right away is it says riff. And then in here it says wave, and then format, and then data. So that's interesting. So at least like we have some footholds. Like now we know like, okay, so maybe like this type of file is called a riff file, and then like the format is wave, and then something. So we'll be going through that. But first I want to, let's try to guess like what's actually going to be in this file. So because wave files store like a lot of information. They have to store like how, like the shape, what the shape looks like of the wave. They might need to store like words in it. So we're just going to kind of try to guess like what's in a wave file. But first, so here is a digital audio workstation. And what's really cool is now we can look at this wave file and see the shape of the wave. And the shape of the wave means that if you connect a speaker to play the sound, then the speaker will take on whatever value the wave is at. So for example, like here, we can see that the wave is high. So the speaker might be like up like this. But now down here, the speaker might be down like this. And so it like alternates up and down, up and down, up and down, up and down. And that's what produces sound, is the speaker just shaking. And that's what creates sound. And if like I could shake my hand back and forth enough, then it would produce some sound. But like this is only like, I don't know, 4 hertz. So that's like way too low pitched. Whereas this, I believe, is 400 hertz or something. So 400 hertz meaning 400 times a second, or 4 hertz happening 4 times a second. But yeah, so if we scroll in more into this wave file, then we can see that there's actually all these dots here. I don't know if you can see, it's kind of small, but like there's a dot here, 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 here. Yeah, there's a bunch of these dots. And so we call each of these dots samples, because so the wave file, what it will do is it will just kind of send its sample to the speaker and say, okay, I need you to be at this location at this point in time. And then the speaker's like, okay. And then at the next sample, it's like, okay, now I want you to move like down a little bit. And the speaker's like, okay. So then it'll like follow whatever the dots say. So this dot says like, okay, be at this position. Whereas this dot over here says, yeah, be at this position. So each of these samples or each of these dots correspond with where the speaker will move. And so as you can see, like the wave file just has tons and tons of these dots. Like a few seconds in, tons and tons of dots. And does anyone have a guess for how many dots there are in just a single second? Anyone have a guess?
Could you repeat the question one more time?
Yeah. So there's tons and tons of these dots right here. So my question is, how many dots do you think happen in 1 second? Like, you think this is 1 second and there's like 100 dots, or maybe like this is a second, or like, how many dots are in like 1 second, do you think?
Well, enough to not cause aliasing, right?
Yeah, right. So it needs to sound continuous. We don't want it to sound like jagged and like low quality. You want it to be a very smooth waveform. And so generally music plays at 44.1 kilohertz, meaning that meaning that there are 44.1 thousand dots per second. So that the speaker is updating its position 44.1 thousand times per second. That's really fast.
That's brilliant.
Yeah, it's crazy. Like, this is just like a tiny, tiny snippet in time. It's just like a tiny little millisecond. Like, look, like this whole clip is 3 seconds, and look how massive, look how many dots there are. Insane. And this is just one channel. This would only play out of like one of your headphones, because like it's only just one speaker. But now let's assume that we have 2 speakers that are all moving. Now you have twice the amount of information. So wave files need to hold an insane amount of information. So that's why wave files are not actually like used all that much for like listening to music, because wave files are massive. Like just this wave file, just this wave file, 258 kilobytes. If I have just like a text file and I like write like hello, that's just like 5 bytes. But this is 258 kilobytes. So not at all compressed. Versus if you had like an MP3, it would probably just be like a few kilobytes, because MP3s are very, very compressed and way better at sending to other people. Okay, so but sometimes you may actually want to not do 44.1 kilohertz. Maybe if you're like on an older speaker, you don't actually need that many data points because the speaker is not actually going to update that much. Or let's say you're doing intense music production and you want it to be as continuous as absolutely possible in case you want to like slow things down or do stuff. So a lot of sound music studios will actually record at 96 kilohertz, I believe. And 96 kilohertz, that is just so many data points. The files are so massive. It's like gigabytes upon gigabytes for just like easy little songs. Yeah. But also, so look at this. So has anyone heard of like 8-bit music?
Yeah.
Yeah. So 8-bit music kind of usually sounds like way worse in quality than like this music, right? The normal music. Yeah. So
I guess it's more limited. Yeah.
Is way more limited. So yeah, and the reason for that is because, so look how many values that each of these dots can take. So this, we call this a 16, this has a bit depth of 16, meaning that, so each of these dots, there are 2 to the 16 different values that they can take on. Versus 8-bit music, there's only 2 to the 8 different values it can take on. And when I say values, I mean like where it moves the speaker to. So like, for example, like a dot can appear anywhere from the very top of this thing to the very bottom of this thing, and like any value in between. And the more like options you have, like then yeah, the more continuous your wave will sound. Versus if you just like, let's consider like a case where you only have 1 bit per dot. So 1 bit per dot may mean like high or low. So if you have a bit depth of 1, then there's only 2 different values that each dot can take. It's either like the speaker is either here or the speaker is either here, but it can't be any values in between. But now let's assume that we have like a bit depth of 2. So now we have 4 different values that the speaker can be at. So the speaker can be at here, can be at here, can be at here, can be at here. So now that's way better than if we had a bit depth of 1. And if we have like a bit depth of 3, then we have 1, 2, 3, 4, 5, 6, 7, 8 different values. Or if we have 2 to the 8, then now we have 256 different values. So that's what 8-bit music is each of these dots are limited in like where they can actually, or in like the precision of where they can move the speaker to. Like 8-bit music can't like move the speaker like very continuously. The 8-bit music is going to like move the speaker like this, and it's not going to be like very fluid. So yeah, that's why 8-bit music sounds like way worse in quality, is because each dot just has fewer values that it can be at. So that's another thing that we need to keep track of, is probably like the bit depth, right? So let's make a list now. So what are some things that WAV files need to keep track of? So like I just said, so the bit depth, meaning like how many bits are needed to store each value, each dot. Yeah, what's another thing that a WAV file would need to store?
Component.
Yeah, exactly. So yeah, you might want to store metadata, like maybe like what the song is called in the actual song, or maybe like, yeah, when the song was recorded. That'd be cool. Okay, yeah, something else. So yeah, we have bit depth, but also probably sample rate, meaning how many samples there are in 1 second. So like, for example, like this case is 41,000. Some may be like way more than that. Some may be way less. So yeah, so sample rate, bit depth, metadata. What's something more generic that like all files should probably like store within them? Maybe like the size of the file too. That could be very useful. So that way, like when you open the file, you instantly know like, oh, okay, so this much is allocated for the wave data.
Oh yeah, another thing I was wondering about is the, I know the frequency can give like the sound pitch, but I don't know about the like amplitude, like the magnet, like the how loud.
Yeah. So amplitude. So yeah, the louder something is, the greater the amplitude is on for like each of the dots. So if you want a really quiet thing, then the dots may just be like really localized, like down here. Versus if you want a really loud thing, then they will the dots will be way more up and down.
Right.
Yeah. So yeah, and another thing, so we probably need to have some large array of all of the different samples. So that's another thing that we need. And maybe also like how many channels there are. So this is just one channel, right? This could come out of like just one headphone. But yeah, let's say now we have like 90% of music. No, 100% of music is stereo, meaning like two headphones or two speakers. So, but we need to keep track of that. We need to be like, oh, is this one channel or is this two channel? Okay, so let's actually look at what the WAV file format is. So, so like you can see here, so num channels. Okay, we talked about that. Sample rate, yeah, talked about that. Byte rate or bit rate, yeah, okay, we talked about that. Block align, not sure what that is. Bits per sample, so bits per sample. So every sample, like we said, like if it's just 1 bit per sample, then it's just like either on or off. But if it's 2 bits per sample, then it's whatever. Then there's 4 different values that it can take on. So yeah, bits per sample. And I guess, yeah, so we can see like chunk size. I'm guessing that's like the file size. So yeah, let's try like going through this file in a hex editor and seeing what's happening.
I'm actually surprised that all that we need to express like all sorts of sounds are contained in this WAV file format.
Yeah, it's very, very straightforward. It's just like a few different things. And that's WAV file, like a great starter project for dealing with binary data and reading it. It's because, yeah, there's just a few like things that we need to keep track of. Yeah, so, okay, let's look at this. So it says chunk ID. So, so I'm guessing here we can see it says riff. So that's probably the chunk ID, okay. And then chunk size. So here it says, yeah, BE0940, okay. So that's kind of cool. Okay, and then here it says wave, and I'm guessing that, so that's like the format of the file maybe. So I'm guessing that maybe like riff is like the style of like this format. Like I'm guessing a lot of different things can have the riff format, but like wave is in like wave is one of those files. Yeah, I don't know, just like thinking aloud how it's going. So yeah, and we can like keep going down, but this is kind of interesting. So look at this. So BE090400. So if we go and type that out, so if we do like OX BE090400 in decimal, look at that. That's a huge number. That's interesting. So yeah, if we like convert this to gigabytes, or maybe like just megabytes. So no, yeah. So it says that this file is 3 gigabytes, but that's not right. Because do you remember it was only like 200, whatever. It was like 200 kilobytes. So not 3 gigabytes. So why the heck does it say that this is, that this is 3 gigabytes? Does anyone have an idea of why this says, BE090400? Because it says, so it says here, so chunk size. So chunk size is the size of the chunk following this number, the size of the entire file in bytes minus 8, basically. So yeah, we should expect it to be like, 25 or 250,000. Yeah. Does anyone have an idea?
Is this because of that Endian thing.
Yes. This is
No.
write it down. So we know that the file is OX49C0 about. So we know that it's this size. But when we scroll up here, it says that it is OXDE0904. Yeah, so look at this. So if we've like put spaces between each of these bytes, yeah, so 04, 04, 09, 09, and then C0B, close enough. So it looks like it's reading the number backwards. And yeah, so I'm like beating around the bush. It's because in computers, generally numbers are actually stored backwards. So even though we would say like, oh yeah, okay, so this number is whatever, 250,000, we instead write it as like 3 million. We write it backwards. And so this is called Little Endian, right here. So Endian, so Little Endian. And what Little Endian says is we want to put the least significant bit or the least significant byte first. So since this is the largest number, we put this last, so the 04, and then we put next like the 09. And then since BE is the smallest number, we put that first. So it's little first. And you can think, so Little Endian is really helpful in computers because the little numbers or the least significant bits correspond with low address values or low offset values. So let me say that again. So this offset is 4, as you can see. And then this offset is 5, and this offset is 6. So it would make sense that your offset, like the smaller the offset value, the smaller the value is for the number. But yeah, so like if I write out and say like the number 123, so we could say that the offset for 1, yeah, we can say like the offset for 3, since it's the smallest number, we can say that it's like 0. And then since 2 is the next number, we want the offset to be a larger number. So we put 1. And since 1 is the largest number because it's like 100, then we would put an offset of 2. So that way the offset number corresponds with how significant the bit is. Yeah, so Endianness just means like some computers store numbers backwards. However, actually quite a few computers store them big endian, meaning like the way that humans read. But some computers do little endian, some computers, oh, actually, wait, before I talk about that, I want to show you this pig, because I feel like this explains everything very well. Okay, that's it. So like I said, there are pros and cons of using each encoding. Like one of them is really easy to read for humans, one of them is easier to read for computers. But the biggest con of all is that we just cannot agree on which one should be used. And that sucks, because it would be really nice if there was just like, oh, right, like we're always just going to use big endian, no questions asked, boom. The problem is that's not true. So we need to ensure that we have some easy way of converting between the two endians. And but what's really nice is all operating systems provide the functions host to network and network to host. So all computer networks, meaning like the internet, so all computer networks use big endian. And one reason for that is because big endian means that the numbers are like the bigger numbers are sent first because like they're more important. So like, let's say we have some number that like is trying to be sent to you, but then they stop sending it halfway. You know, like, oh, well, like at least you know like what the first few bits or what the first few bytes are. So now you know like, oh, okay, it's actually like, it's in the ballpark of this range. yeah, so like, let's say you're sending like 386 and someone sends, all right, 300. And you're like, cool. Okay. What's the next bit? And then they're quiet. They're like, okay, so I know it's in the ballpark of 300. So that's not too bad, because networks are super inconsistent. Maybe like they might break up at some point. So versus if you were to say like, oh, all right, first I'm telling you the least significant bit is 1. And then like they stop talking. It's like, okay, I don't know at all like what could happen. Like I don't know how much space to allocate now. Yeah. So overall, yeah, fantastic idea to use big endian for networks. However, most computers use little endian. So all operating systems like Windows, Mac OS, Linux, all have the function host to network and network to host. And so now, so host means like the computer that you're currently writing code on. So if you are writing code and it's all in little endian, and then you say, okay, I'm going to call host to network, then now your memory will get swapped. And now it is in big endian. And then now you can go and send it out on a network and you're super happy. But now let's assume that you're writing code on a big endian computer, like maybe like the Nintendo 64, it's big endian. Then yeah, when Nintendo 64 says, all right, now I want to convert my code to the network code, it doesn't need to do anything, but it'll still run this function, and this function will say, oh yeah, don't even worry about it. You don't even have to do anything. I'm just going to send the message as is. Versus an Intel machine is going to see that it's like, okay, you just called host to network, so that means I got to convert it to big endian. So I got to flip all the bytes. But as a software engineer, it's really nice because all you have to do is just call host to network. Sometimes it'll be flipped, sometimes it won't be flipped, but at least you know that the output will always be big endian. Okay, yeah, hopefully that makes sense. But what's kind of unfortunate for us is all WAV files use little endian for all their numbers, and they only use big endian for like the words. So they use little endian for numbers. So what I did here is I made some macros for us. And so now, yeah, we can call, so here's a function that I created called host to big endian, which is just going to call our host to network function, easy. And then, and this L stands for like long or 32-byte thing or 32-bit thing. And then here's short, meaning 16-bit. So yeah, this is host to big endian. But then also we have like host to little endian. So it's the exact same thing as host to big endian, except we run this endian swap function that our compiler gives us. So these macros, what's really cool is now you can run. So you can run this like host to network function, but then also you can either get big endian out of it or you can get little endian out of it. So this is a way that we can get the endianness of our computer and convert accordingly, even without knowing the endianness of your computer. You can just call this function, and now you automatically just have an endian converter for you. So yeah, this is going to be extremely helpful. And anytime you ever write any sort of binary data thing, you always want to be super mindful of your endianness. And so this could be super helpful. And I totally give you permission, if you're ever needing to use this code ever again, you are totally allowed to steal these macros and use them in your own code. All right, I'm going to give you a little test. Okay, so let's assume I'm on Nintendo 64. What endianness did I say that the Nintendo 64 has? Do you guys remember? Big endian. Yeah, okay, so N64 is big endian. And so what happens if, so on N64, int x equals like ox. Let's not do it. Let's do it like int 16. Okay. So 0, 0, FF. Okay. So what, in memory, what does 0, 0, FF look like in big endian? Can everyone put in the chat, maybe private message me? What does, on the N64, what does 0, 0, FF look like in memory? So, so it would be, so in memory, and so this, yeah, in memory, it would look like 0, 0, FF. Cool. And so the reason for this is because it's big endian. So this is the most significant bit. And then this is the least, most significant byte, the least significant byte. So we store them in that order, most significant to least significant. All right, now let's look at the M1 Mac, which is little endian. So what would it look like in memory? So yeah, if it was big endian, it looked like this. So now what will it look like if it's little endian? Yeah, so remember, like little endian means that the most significant byte is last and the least significant byte is first. So in this case, it would be, it would be FF00. Okay. Okay, so let's do another test. So now let's say, so we're gonna stay on little endian, but now let's do int 32. So now there are 4 bytes here. So let's do AABB. Okay, so now what will this look like in memory? Yeah, so the way we convert this to little endian, so yeah, we start with the least significant byte, so FF, and then we go down the line, so 0, 0, and then BB, and then AA. Cool, okay. And okay, now let's do one last one. So yes, still M1 Mac, but now let's do int 64. So now there's more bytes. And no, you know what? Let's do N64. So big endian. Yeah, okay. So now, now that it's big endian, how do we write out the same number? So how do we write out this number in big endian?
Because it's N64, do we add all the zeros on the left side of A?
Yeah. Wait, yeah, that's a very good point. Yes. So this, since this is an int 64, there are a lot of implied zeros here. Yeah, so can you guys go and try to write out the implied zeros? Because remember, int 64 means that there are 8 bytes total. So somehow we need to have like all 8 bytes in memory. So yeah, so I can tell you like the first byte is going to be 0, 0. And then next byte is 0, 0, 0, 0, 0, 0. And then it's just going to read this like just the way that it is. So since it's int 64, so there are 4 bytes here, 4 bytes here. Wait, does this make sense, or do you want me to go over it again?
No, I think it makes sense. You just add zeros because it's like, it's a bigger byte. I get, oh yeah, 64 bytes.
Right, 64 bytes. Yeah, so it's or 64 bits. So yeah, it's 8 whole
so
bytes.
you're just adding, are the zeros just like spacers or like
exactly?
Yeah, spacers.
Yeah. Okay, so now let's do. Wait, Eric, can you walk me through how to do it for little endian?
Little endian.
Yeah.
Would you just have for which one?
For this one right here. So Yeah. So
Please
I have an int 64 right here, and this is what it looks like. So can you tell me, how to write it out?
Would it just be FF00BBAA and then the last four is just zeros?
Yeah, exactly. Awesome. Yeah, okay. I feel like we get it now. So good work. Yeah, okay. That's basically Endianness. So yeah, so these, but you don't really need to know this super well. All you need to know is just like always use these functions right here whenever you need to, whatever, mess around with Endianness. Okay. All right. Next, I want to just show you the starter code. I'm thinking we may not have time to actually write much code today, so maybe we'll do it just next week. But let me show you, the starter code. Okay. So, so step one, you uncomment. Yeah, we can run make. Cool. And so, yeah, it compiles. So, yeah, let's just look at this main really quick. So this main says, okay, so takes in, args. And so in here we say like, oh, if args is less than 2, meaning if a value is not plugged in, like if we just run /main, then it'll say error did not give file name. So we need to give it some sort of file name. So we can give it file name of tests and then 41. What? There we go. Yeah, okay. And then we can see like that there's some mistake. So, yeah, step one. So we are making a WAV file from the file name that we plug in. So argv of 1 just means like this parameter right here that we put in. And so once we call this constructor, so let's go to the constructor. Yeah, okay, so the WAV just runs load. So here's the constructor. So it takes in a file name and then it loads the file name. So now let's go to load. So yeah, so we can see load. So load needs to take in a file stream or needs to initialize a file stream. And this file stream will take in this file that we've called in file name. And then we need to somehow like open this file and then so we get the size of the file and then create a buffer based off of the based off of the file. So now the file is going to be in this massive 2D array, and it's going to every single value of this array is going to be like every single byte. So so buffer is going to hold all of the bytes of our array. So I'm going to pull up my iPad just and I'm going to show my screen on my iPad. So yes, like I said, so we're going to have this buffer. And this buffer is going to be made up of a bunch of bytes. Yeah, like I don't know, 0, 5, A0, 3, 6, just a bunch of bytes. And then I like every few points, like I don't know, maybe like these 4 bytes correspond with like a sample, or maybe these 4 bytes correspond with the sample. And so the way that we can like get each, we can load like the sample data from this buffer. So if we say like int, whatever, x. So what we can do is we can just call memcopy. And so it goes destination and then source and then size. So this is like the header for it. Meaning, So destination. So if we wanted to copy, let's say we wanted to copy like this. Oh my gosh, no. Okay, let's say we wanted to copy this section right here. So so ints are 4 bytes. So if we wanted to copy these 4 bytes into this int, then we could just call memcopy. So let's do that. So does anyone have an idea of what we would put as maybe like the destination? So what would the destination be in memcopy?
X.
Yeah, it'd be X. Yeah, be X. So and it would actually be like ampersand X because we want to get the pointer to X. Yeah. Okay. And then so what would the source be? Does anyone have an idea? Yeah, buffer. And what's the size?
Would it be 4?
Yeah, it'd be 4.
Okay.
Exactly. Yeah. And if you want, you could do like size of X. But yeah. Okay. But here's a question. Are we done? So like we loaded it into X. Fantastic. But what did I just spend like half an hour talking about?
Big Endian, little Endian.
Yeah. Endian. So how can we ensure that we have the correct Endian here? What should we do? Well, we got to like convert it. So we got to say, so we know that this buffer, let's assume that this buffer is little Endian because the wave file will be little Endian. So if the wave file is little Endian and we have, let's say we have a function called like host to little Endian, and we also have little Endian to host. So which function could we call? Like let's say, so X is equal to like some function, and then we just plug in X as like the input. So which one should we call?
Oh, which one do we want X to be? Big Endian? I mean, it depends on the situation though, right?
So yeah, so we want X to be host because the whole point of this is so we always know no matter what computer you're on, wave files are always going to be little Endian. However, now let's say we want to compile our code on an N64, which is a big Endian, or we want to compile it on the M1 MacBook, which is a little Endian. So we want the host to be whatever X is.
In this case, I think it will be little Endian to host.
Exactly. Exactly. Because so we're copying it. We're copying this little Endian value into our memory. And that could be correct. I don't know, could be, or it could be wrong. So what we just do is we call this little Endian to host because it says that this is little Endian, but we're just going to convert it to what our host does anyways. Because maybe if the host is little Endian, it just won't do anything. No conversion will happen. Cool. But if it's big Endian, then a conversion will happen. So this is going to be kind of like your bread and butter of loading data. Is first you copy it, and then you go and correct its Endianness. So copy, correct Endianness, copy, correct Endianness. All right, so now let's try loading maybe like, so if this is 0, 1, 2, 3. So now we want to try loading like this section. So like 4, 5, 6, 7. Let's say we want to load that into Y. So how could we load that into Y? So int Y. So what's the first thing that we do? Remember this? So what's the second one? Yep, memcopy. Okay. And what do we put in here? So what's the destination?
Would it be ampersand Y?
Perfect. Yeah.
Or would it just be Y? Okay.
Ampersand Y. Yeah. Sorry. What's the
buffer,
source? Right? So it's almost buffer. But look at where buffer is pointing. Buffer is a pointer that points right here.
Oh, okay.
So what can we do?
Would you put like a bracket to show like where in the buffer or no?
You could also
Sure.
add numbers, right?
Yes. Yeah, that's what I'm looking for. So yeah, as Drop said, so we could do like maybe like we could do like buffer of 4, but then maybe like ampersand. So this will get us the address at the 4th location in the buffer, which totally works. Or we could just kind of like make it a little bit like cleaner, and we could say buffer plus 4. And so now we take buffer and we basically just like move this guy over. So now the buffer is actually like over here. So now the buffer like points right here instead. So buffer plus 4.
I'm
Mm-hmm.
a little unsure why the adding works. I've seen it before. I forgot why it works.
Yeah. So remember, so actually buffer is just a number. It's not actually this big old array. Buffer is just a number. It's actually an integer.
Oh, it is. Okay.
And yeah, and so the integer just means where in memory, like, should I care about? Like, yeah, what memory location should buffer represent? And so buffer is just representing this. So it's an integer and it represents this memory location. So if we do plus 4, then we're just going to increase the memory location. Let's say like we do plus 1, now buffer is just pointing at this memory location. If we do plus 4, then now it's pointing at this memory location. But let's say now like, yeah, if we wanted to like subtract 4, then we just boom, like move it back like this. And now this, now buffer points to the start of this array. Or yeah, start points to the 4th element. Okay, so what now? So we did buffer plus 4. So what's the next thing that we put in?
Size of
Y.
Sure.
Yeah.
Yeah, sorry, I'm writing fast. My handwriting's kind of bad. Cool. Okay. So yeah, this is going to be our bread and butter. So let me go back and share the code. We'll stop in just a second. And then, yeah, then next week we can start writing some code. Yes. Okay. So yeah, here we can see buffer. So buffer, new int, buffer size. So buffer size is, yeah, whatever. Cool. We'll do this next week. So load little endian says, okay, so get the length of the destination. So yeah, if it's like X or if it's Y, so get the length of the size of the destination, and then mem copy into the destination from buffer plus some offset. So it might be like plus 4 or it might be plus 8 or something, but yeah, plus offset. And then the length is just this guy. And then here, so we say, so it's a switch statement. So it says, so if the length is just 1, then it doesn't matter if it's big endian or little endian, because like you can't like move that anywhere. It's just 1. But now case 2 is if now there are 2 bytes. So if there are 2 bytes, then we want to call this function, but this is like the 2 byte version. And if it's 4 bytes, then we want to call this function, which is for 4 bytes. And then if it's anything else, then we just throw bad size. And then after that, we increase the offset. So now the next time we ever call this load little endian function, it will just move the offset. So it won't load the same place twice. So yeah, I'll go over this again next week because this is more starting to get into the code. But yeah, but this is just following exactly what I just said, like with the iPad and what I drew out. So you can look at this, and it's similar for the write little endian function, where it's mem copy, except you're copying it into the buffer from the source versus like from the yeah. Anyways, okay, cool. Yeah, class is over. If you want, you can start. You can get started on like working on the starter code. And if you want, like you could try doing this project without using any starter code, because that might be like super fun. I did it, no starter code. So it's totally possible, but it's also a lot of work. So up to you.